Okay. So, time complexity part over. Next we will be analyzing the success probability. That is a crucial part of the Monte Carlo algorithm. So, probability analysis. Okay. Well, I will assume that K be a size of a min cut. In the graph G. Okay. Now, what about the number of edges in the graph? Assume that there are n vertices. When K is actually the size of a min cut, what could be the number of vertices? Can you give a bound for that? Sorry, number of edges in the graph. Why? You can make use of the simple handshaking lemma. Okay. You are using the result 2e equal to summation I equal to 1 to n degree of Vi. Am I correct? Good. See, since min cut size is actually k, degree of each and every vertex in the graph should be greater than or equal to k. If it is one vertex degree is less than k, by removing that one itself you can disconnect the graph. That edges alone you can disconnect the graph. Then the min cut size will not be k. So, number of edges in G is greater than or equal to kn by 2. Now, we will define some events. Okay. Let Ei be the event that ith iteration does not contract any edge of C. C is min cut. Okay. Now, can you define probability of success? In terms of Ei. In the first iteration, none of the min cut edges are contracted, correct? Second iteration does not contract any edge of the min cut. So, if it is followed in all the iterations, finally you can get the correct answer, correct? So, what is needed in terms of Ei? Totally how many iterations? N minus 2 iterations, correct? So, first iteration does not contract, and second iteration does not contract, and third iteration does not contract, and finally the last iteration also does not contract. So, what is needed? Intersection probability of intersection I equal to 1 to n minus 2 Ei. Okay. We have to estimate this probability. This is the success probability. So, first we will start with E1, probability of E1. For that, first I will find out probability of E1 complement. Okay. What is E1 complement? One edge of the min cut is contracted by the first iteration, correct? So, probability of E1 complement is anyone? Now, you can make use of the basic probability formula, probability of an event, number of favorable cases for that event divided by total number of cases, correct? So, if I choose one of the min cut edge, that is out of this k edges, if I choose one edge in the first iteration and contract that one, it is a failure, correct? So, what is the numerator? Kc1, correct. What is the denominator? K, totally there are number of edges is greater than or equal to Kn by 2, correct. So, this is less than or equal to Kc1, so K divided by Kn by 2, which is equal to 2 by n, okay. So, probability of E1 is greater than or equal to 1 minus 2 by n, since it is a complementary event, okay. Now, when you consider probability of success, it is the probability of intersection of all these events, okay. How many of you know total probability law? All of you know? So, this could be written as probability of E1 into probability of E2 given E1 into probability of E3 given E1 intersection E2 etc. into probability of En minus 2 given intersection j equal to, already n minus 3 iterations over, so n minus 3 Ej. Am I correct? Okay. So, we have to estimate these probabilities and multiply. Probability of E1 is greater than or equal to 1 minus 2 by n. Now, consider probability of E2 given E1. This is greater than or equal to, can you tell me? 1 minus 2 by n minus 1. Okay. Similarly, we can generalize this one and write probability of Ei given intersection j equal to 1 to I minus 1, already I minus 1 iterations over. So, Ej, can you tell me, is greater than or equal to, just generalize it, 1 minus 2 by n minus of I minus 1. Okay. Now, you compute the probability of success. It is greater than or equal to, first term probability of E1 is 1 minus 2 by n, then into one minus 2 by n minus 1 etc. What is the last term? Two by n minus it is not in terms of I, correct? That is a general term in between. Last one is probability of E n minus 2 given intersection of 1 to n minus 3 already over. So, what is the probability? 2 by n minus, you can make use of this one. What I have to do is substitute I equal to n minus 2. So, if I substitute, it is 1 minus 2 by n minus 3, n minus of n minus 2. So, 2 by n minus 2. You are able to understand? It is not clear? So, I will go back to the previous slide. Probability of EI intersection, this one is given this conditional probability is greater than or equal to 1 minus 2 by n minus I minus 1. In the probability of success, last term is probability of E n minus 2 given. correct. So, in this expression if I substitute I equal to n minus 2, I can get this probability. If I substitute I equal to n minus 2, 1 minus 2 by n minus 3, that is what I told first, okay, n minus 3, okay. So, you simplify, this is greater than or equal to n minus 2 by n into n minus 3 by n minus 1 into etc. Last term is n, you can cancel 3 minus 2 which is 1 by 3, okay. So, if you see the terms here, the next one will be here n minus 4 by n minus 2 etc. So, you can cancel many terms, okay. What will be the remaining terms after cancelling the factors there? 2 by n into n minus 1, okay. You can cancel n minus 2 like this, then n minus 3 here and n minus 3 like this you can cancel. So, here you will be left out with 2 into 1, then divide by n into n minus 1, which is greater than 2 by n square. So, computational complexity of the algorithm is order of n square for a single run. Kargar's min-cut algorithm outputs a min-cut with probability at least 2 by n square. We have analyzed these two, okay. Now, for example, your n equal to 100, you can consider a graph with 100 nodes. What is the success probability? Or you consider a graph with 10 nodes, success probability is 2 by 100, correct. So, it is very less. Can you be happy with the algorithm? No. So, how to improve the probability of success? Okay. So, one run of the algorithm is not actually favorable to me. I am not very happy with the outcome of the algorithm. Can you improve the probability of success? What I have to do is boost the probability of success, okay, to get a good number. Repeat the algorithm, okay, with a different choice of random numbers. If I repeat the algorithm t times using fresh random bits, I will be having different outcomes, correct. In the previous example, when you run the algorithm once, you got the min-cut size as 3, in the second run you got the min-cut size as 2, correct. So, when I repeat this algorithm, f1 is the outcome of the first run, f2 is the outcome of the second run, like that ft is the outcome of the tth run, correct. Now, you output the minimum among these fi's, okay. When the number of runs is more and more, you can get a success probability as high. But what happens to the running time? You can repeat it, no problem. What about the running time? It is also going on increasing, okay. So, running time of the algorithm, when you run it n square by 2 times, you see probability of failure is 1 minus less than or equal to 1 minus 2 by n square. Probability of success is greater than or equal to 2 by n square for a single run. So, probability of failure is less than or equal to 1 minus 2 by n square for a single run. If I repeat the algorithm n square by 2 times, the probability is of failure is less than or equal to 1 minus 2 by n square the whole power n square by 2, which is less than 1 by e, okay. So, probability of success is greater than or equal to 1 minus 1 by e. 1 by e, what is the value? It is 1 divided by 2.7 something. So, it is little bit better, am I correct? So, it is a constant success probability bound. Okay, you are able to improve the probability by running the algorithm so many times. Okay. What about the running time of the algorithm? For one run it needs order of n square time. If I repeat the algorithm n square by 2 times, order of n power 4. Do you prefer the algorithm? It is not better than Ford-Fulkerson algorithm. Okay. You have done lot of work, but the algorithm is a very simple algorithm. Easily you can implement the algorithm, but when you do the analysis, to get a better probability bound for the success, you are repeating it so many times. So, the running time of the algorithm is order of n power 4. It is not better than that Ford-Fulkerson algorithm. Now, can we do better? That is the next question. Naturally, that question will arise. Now, to improve the probability of success and at the same time to reduce the running time of the algorithm, what is to be done? Now, I will give you a hint. Think in terms of the height of the computation tree. For the computations, you can draw a binary tree, correct? Recursive calls merge sort, correct? You have learned merge sort, you will be drawing a computation tree, correct? Similarly, if you draw a computation tree for this algorithm, what will be the height of that tree? Just try and tell me. You are starting with n node graph, correct? Then you are doing one contraction, correct, which reduces the number of nodes to n minus 1. So, root of the tree with the n node graph. One computation there, that is one edge contraction, gives you an n minus 1 node graph, correct? And you can stop this iteration when the number of nodes in the graph is 2. So, what about the height of that computation tree? N minus 2, correct? It is in order of n. Okay? Can you reduce the computation tree height? If I can reduce the computation tree height, correct, I can reduce the computational complexity of the algorithm. Are you able to understand? So, if you consider a binary tree, what is the minimum height of a binary tree? Order of log n, okay. If I can reduce actually the height of the computation tree to order of log n time, then among the n square leaves of this one, order of n square leaves, the correct answer occurs somewhere, okay. So, you can output the answer at the one of the leaf node as the correct min cut, and at the same time you can reduce actually the height of the computation tree, which reduces the computational complexity of the algorithm. Okay. Now, tell me how to reduce the height of this one. What is the problem there in your Kargar min cut algorithm? Dividing it by 2, that is contracting 2 edges simultaneously. The major problem in that one is why the computational tree height is order of n. You start with the n node graph and you are waiting till you get a 2 node graph, correct. So, if I can stop this iteration a little bit earlier, instead of reducing that one to 2, if I can reduce that if I stop the number of iterations a little bit earlier, then the height of the tree will be reduced, correct. Are you able to understand? So, that is the next development which gives the fast min cut algorithm, okay. This is again by Kargar and Stein, okay. After analyzing all this, they are able to give a fast min cut algorithm by reducing the height of the computational tree, okay. Then one more thing is, just you have noticed in the analysis, probability of contracting an edge from the min cut in the first iteration is less than or equal to 2 by n, correct. But when you reduce or contract one edge and move to the second iteration, whether the probability of contracting a min cut edge is increasing or decreasing? Take n equal to 10, correct. Just work out and see. You are having the probability expressions. Probability of contracting an edge, okay, min cut edge in the first iteration is less than or equal to 2 by n, okay. If you assume n equal to say 100, so this value is less than or equal to, or you assume n equal to 10, easily you can finish it off. 0.2. What is the second iteration? probability of contracting an edge of C in the second iteration. Use the expressions. See, probability of E1 complement is this one. Probability of E2 given E1 is this one. So, probability of E2 complement given E1 is 2 by n minus 1, correct. So, use that one and do. What is the value? Zero point. Why no answer? 2 by n minus 1, 2 by 9, am I correct? So, 0.22. Now, see, if you proceed like this, when only 3 nodes are left out, what is the probability of contracting a min cut edge? Whether it increases or decreases? It increases, correct? See, when you are having 50 edges, probability of choosing one min cut edge is less, correct? When you are having 49, it is little bit greater. When you are having 45, among the 45 you have to select. So, probability of contracting a min cut edge is slightly more. When you are having only 3 nodes and some edges there, probability of contracting a min cut edge is more, correct? So, what happens is when I reduce that one to a 2 vertex graph, finally the probability of contracting the edge is increasing slowly, correct. So, this fast min cut algorithm reduces the height of the computational tree, and at the same time it does not allow to increase the probability of failure when you proceed. So, properly I have to choose the value of for terminating the algorithm, correct. You are able to understand how to choose the value is a tutorial problem, okay. So, in the next class, I think we can discuss this fast min cut algorithm. I will just explain this one. Only way to succeed, it is by increasing the success probability, that is failure probability is going to be decreased, correct. But in the Kargas algorithm, the failure probability is also going on increasing. We have to decrease that one, and the crucial insight is when you take actually that binary tree, if you are going to do iterations that is 1 by 1, then definitely the height is going to be somewhat order of n, correct. So, in parallel or simultaneously if you can do 2 iterations there, then you can actually reduce the computational complexity. So, this algorithm I will be discussing it in the next class. What's the time now? Any questions? No question? Everything is very clear or nothing is clear? Only 2 possibilities. See, I expected this question when we discussed this Kargas min cut algorithm itself. In the algorithm, you can either you write it as a for loop or you can write it as a while loop. Am I correct? While cardinality of v greater than 2, do that one. Pick a random edge E from G, correct? Then contract the edge. How do you conclude that? The running time of that algorithm is order of n square. For each contract algorithm, we need order of n time. What about that pick a random edge? What is the running time of that one? None of you asked about that one. You are having m edges in the graph. When you implement the algorithm, you will be implementing a rand function, correct? That 0 to m minus 1, you can generate any number there, or 1 to m you generate a number, random number. Always in the randomized algorithms, we make the assumption that random generator or random number generator takes only a constant time to generate the numbers, correct? So, we are not actually choosing any edge from the m edges, correct? Then MC1 possibilities are there, the running time is going to be order of m into, okay? We use a random number generator, use rand function, get the value of that one, pick that edge and contract that one. So, it needs only a constant time there, that is the reason it runs in order of n square time. Okay. See, this area, even though the research has started very early, it's lot of research is going on in the design of randomized algorithms. The latest trend is randomized machine learning algorithms, randomized SVM, randomized decision tree. Okay. And in designing games also, randomization is used. In cryptographic applications, randomization is used. So, it is really a very good research area, and you will be enjoying the probability analysis when you start to read this one. Both are equally good, but one thing is, see, to coping with the NP complete problems, you are going for either parameterized complexity algorithms, where you will be fixing some parameter and the complexity of the algorithm and design the algorithms. Am I correct? Here, without fixing anything, you will be designing a randomized algorithm, correct, and analyze its probability of success. What I have to decide is how many times I have to repeat this algorithm to get a good probability of success. Right. Nothing is initially fixed. Okay. So, just like that, you design the algorithm with the hope that it should run only in polynomial time. If it runs in exponential time, throw it away. Do not use that one, it is of no use, correct. So, there is nothing to fix initially. Just like that, randomization is very simple. In many of the algorithms, you take the deterministic algorithm, include one random number generator and make the choice as a random one. That is the reason actually it is preferred, very easy to design, very easy to implement. Okay. But only difficult part is the analysis, where I have to deal with the probability analysis and the computational time complexity analysis. Otherwise, randomized algorithms are much preferred because of its simplicity. I would like to wind up the session. Thank you so much.